And yesterday we looked at Newton's first law. And that was my object in motion. We looked at Newton's third law. And that said that forces act in pairs. And we're going to start with this, that forces act in pairs. So I'm going to draw something here. I'm going to use my inclined plane. And I'm going to give myself an angle here. And I'm going to draw an object on my plane. And I can actually do this a little bit. Let me give myself an item here. I'm going to use a notebook. So I'm going to use a notebook, and I'm going to put my mouse on the notebook. And so this notebook currently is horizontal. So my angle here would be equal to 0 if I were doing my angle. And I'm going to do my inclined plane here. And I'm going to raise up. Well, that was actually too slick. So let me change. Let me do this. I'm going to use my eyeglass piece here. So I have an object on here, and I can raise my, changing my angle. And as I change my angle, that my eyeglass case stayed in place until I reached what we call a critical angle. So I've got it staying in place until I reach there, and it will start to slide down. Now, the reason I did that is because we want to talk about the forces that are in place. And we want to talk about our things that keep our forces in there. So we want to do what we call a force body diagram or a free body diagram. You'll see it interchangeably out there, but what we're going to do is we're going to draw the forces on our object. Now, we talked about contact forces and we talked about field forces. So we know that we have a force due to gravity, and that force due to gravity is acting in this direction, and we can represent that force due to gravity with an F sub G. Now, one of the things that we know, if you've ever watched the cartoons, okay, or you've gone out to something like park or Zion National Park or someplace out in the West, you'll see something that looks like this. You'll see these great big balancing rocks. These rocks will be balanced out there, and it looks like this rock should fall over, but it doesn't. Because one of the things from Newton's laws is that all the mass is going to act like it's going through what we call the center of mass. And we're going to see in a later chapter actually how to calculate that center of mass. But as long as this center of mass is over the point, over my shelf here, this object is not going to fall over. And we've been able to see that. I mean, I can balance, if I can put my finger underneath the center of mass of my object. Not doing a very good job here. But we can find that balance point for our objects. And as long as I've got my finger under the center of mass, my object's going to be stable. And so we can assume and play with these systems as if all the mass is acting in that spot. So as long as my force due to gravity is supported by this cliff here, and this cliff is able to support it because of its strength, I'm going to be able to keep my center of gravity. So I have my force due to gravity. Now, we know that forces act in pairs. So if my tabletop was here, and I had my object with my 0, right? My 0, there's my force due to gravity. We could use that Newton's third law to give us something else. And we could actually write the force that's perpendicular to my table. And we're going to call this the normal force. And we give it an n. It's still a vector. And we can have the normal force. But if I'm on this inclined plane, my normal force is going to be perpendicular to the surface. So my normal force is going to look like this. Now that makes for some interesting things that happen. Okay, I'm going to give myself some extra diagrams here. So I have this line here. There's my perpendicular. So that's my normal force that's coming into play. Well, this is one of those times that when we talked about it earlier on in the semester, we said we want to be able to move our triangle, be able to play with our triangle and do a few things, because what we're wanting to look at are the forces that are going to be parallel to the plane and the forces that are going to be perpendicular to the plane. So I like to write forces perpendicular and forces parallel. So if I do that, then what I have to do is I have to break out this force due to gravity into its 2 individual components. And this is my force due to gravity perpendicular. And this is my force due to gravity parallel. Now, you can go through and go back to your geometry class. You can go back and prove it to yourself. You can go look at your trigonometry book or whatever, but it turns out that this angle right here is the same angle as that one. And we can play with that and play with our triangles and do all kinds of theory postulates, but we know that that angle there is going to be equal to that angle there. So my force due to gravity parallel is going to equal my force due to gravity. This is the opposite side. So this is going to be sine of the angle. And my force perpendicular is going to be the force due to gravity cosine of the angle, because that's the adjacent side. So if I were writing this out, I've got my force due to gravity and I've got these pieces there. So I can write my components of my inclined plane. The other thing that we have is as long as this is stationary, I have to have another force, because obviously I've got a force that's trying to push my object down the inclined plane. But in order for it to not be moving, I have to have a force that's in pairs coming from that. And that is our force due to friction. And we usually use a script F for our force due to friction. And so now I've drawn a force body diagram for a pair or an object on a inclined plane so that we can still see where all the forces are. So when we do a force body diagram or a free body diagram, we're drawing in our forces. Now, a couple of things. One, yesterday we said that my forces had to be proportional to the mass. And this was coming in our idea of inertia. We also said that my motion that I was going to have was related to the sum of the forces, and this was going to give me my motion. And it turns out that we can look at this, and this is what's going to give us our second law. Now, I'm going to tell you, I don't like, we teach it in this order because physics does this. Physicists are locked into tradition. So we start with kinematics, we end up with forces, and we go on. And if you think about it, we could explain how fast a horse could go. We could explain all of that stuff before Newton came along. And Newton comes along in the 1600s, and we start looking at this. And so now we're going, okay, so we kind of teach it in terms of a timeline and a history. But we also do something just a tad bit out of order. Because one of the things that Newton does, and by the way, you have links to Newton's libraries in Blackboard. You can actually go see Newton's manuals and notebooks, and you can actually read it. It's not the most consistent speller, but you can read all of his stuff. And you can actually look at how he derived these things. It's wonderful. But Newton actually said, well, wait a second. So let's look at it from the idea of a hockey puck. So a hockey puck or a soccer ball or something along those lines, that I can give my hockey puck a whack. So I'm going to apply a force. And if anyone has ever bunted a ball, kicked a ball, slapped a hockey puck, bounced a ball off the wall, we know that the action of our object is related to how much time we have in contact with our object. So we're going to apply a force, and we're going to apply a force over a little bit of time, and we're actually going to call this an impulse. And we really wait to define impulse until after we go through forces and energy, and then we come back and look at momentum, and we define impulse. But if you think about it for a second, we really want to look at this idea of impulse, because this is what saves us in terms of a car. This is what saves us when if we crash into a cement barrier. It's this idea of this changing in the time that really makes a huge, huge difference. And we know it impacts how we react to things. So what Newton really said is that an impulse was equal to a change in momentum. And so, yeah, I'm skipping ahead a couple of chapters, but I hate to just give you Newton's second law, because we do this to you all the time. We're lying to you. Okay? We start out and we tell you Newton's second law is such and such, and that's not really the case. The Newton's second law that we're going to be using in this chapter is actually a special case, and we really want to understand where that comes from. So this idea of change in momentum. So if we think about it, if I throw a rubber ball into the wall, it's going to bounce right back. And we have what we call the law of reflection. If I throw that ball, it's going to reverse and it's going to come back. And momentum, we're actually going to define momentum as this. We're going to define it. We're going to use a lovely P. It is a vector quantity, but it's actually the mass times velocity. And we see this idea of momentum happen a lot. So if I'm sitting in the car and I slam on the brakes and I have my coffee cup sitting in the passenger seat, an object in motion remains in motion unless acted upon by a force. Unless the seat belt's there to stop it, that cup's going to keep on going until it hits into the glove box of the car. Or that's why we always throw our hand out to make sure that the kiddo, who may or may not be seat belted, is in there. So that seat belt in our car is restricting this change in momentum. So if we've defined impulse as force times my change in time, and we're looking at it as a change in momentum, that's a pretty cool idea. Now, we're going to play a mathematical trick. Now, this change in momentum turns out that it can be mass times a change in velocity plus velocity times a change in moment or times a change in mass. And then I'm going to take another mathematical trick and I'm going to divide both of these by the change in time. All right. Well, if I do this, this becomes mass times acceleration because we've defined that as acceleration plus velocity times the change in mass over the change in time. And that's equal to my force. And again, we're dealing with vector quantities here. So if I have a ball and I'm throwing it in the wall and it rebounds, I haven't changed the mass. So a change in mass over a change in time in that case is going to be zero. It's going to be zero. I'm in a truck, okay? I'm in a truck. I'm going to draw my truck here. There's my truck. And I'm going down the road. And my truck has a mass of 4,000 kilograms. And I've got a gas tank or a diesel tank in my truck. And my diesel tank is, let's go ahead and say it's 25 gallons. And I do, and look it up, it's like 6.6 pounds per gallon. And it's 2.2 pounds per kilogram. It's like 2.24 pounds per kilogram. This is approximately, a full tank of gas is approximately 74 kilograms. Let me do that. 2.5 times 6.6. And that gives me pounds. I'm going to divide that by 2.24. Yeah, that's about 74 kilograms. Well, 74 kilograms over 4,000 kilograms is equal to 0.02%, or about, no, it's about 2% or less of the car's mass. So if I'm over a short distance, I'm not changing very much. So I can look at this term, this particular term, as approximately equal to zero for many cases. In fact, most cases. I can't do it if I'm doing the space shuttle or the SpaceX or something along those lines. I can't do it for those because those are, you're changing your mass over time pretty quick. But most of the time, this term is going to be zero and I don't have to worry about it. So we get the common form of Newton's second law. is that the sum of my forces is going to equal mass times acceleration. But I wanted you to see exactly where that comes from. It is a special case. And we'll come back to that special case later. So the sum of my forces is mass times acceleration. But let's look at this part for just 1 second, because we want to talk about that. So I'm in a car and I'm traveling at 60 miles per hour, which is 27 meters per second. And we're going to be nice and we're going to say my car has 3,500 kilograms. And we're going to hit our concrete pillar. And my change in time is going to equal 0.001 seconds. All right. We want to know the force that's being applied. Well, the car's going to hit there. This is going to come back. And depending on how I deal it, the force being applied. So my force is my change in time is equal to my change in momentum, which is the mass times my final velocity minus my initial velocity. My final velocity is going to be 0. My initial velocity is 27 meters per second. So my change is going to be 3,500 kilograms times my 27 meters per second divided by my change in time, which is 0.001 seconds. The force that's going to be applied is 3,500 times 27 divided by 0.001, and it's going to be 994,500,000 newtons, because what we're going to say is a kilogram meter per second squared is defined as a newton. Now, if I put those drums in front of there, instead of just hitting the concrete barrier, what that does is it changes my change in time. And now my change in time becomes 0.1 second. Look what happens. The force that's being applied, 3,500 kilograms, 27 meters per second, divided by 0.1 seconds. I've reduced the force that's being applied onto the car by a factor of 1,000. So it's really important on this impulse side to start seeing that piece. And we're going to come back to dealing with momentum in a little bit, but this is really the idea behind that. So basically, I've got my summation of forces is equal to mass times my acceleration. And this is the common version of Newton's second law. We also have already seen friction. And friction is actually going to be a coefficient. This is something that's empirically measured. times the normal force. So my force due to friction is a coefficient of friction, and I can have two coefficients of friction. I can have coefficient of static friction, and that's the friction that keeps my object on my inclined plane until it breaks. And then I have a coefficient of kinetic friction, and kinetic friction is always less than static friction. We always know it's harder to get something moving because we're overcoming a higher friction than it is to keep it moving. So that's one of the things that's there. We have another force that we need to deal with, and that's Hooke's law. And Hooke's law relates to a spring. So if I have a spring, and if I have a spring that's unstretched, it has a length 0. Then I'm going to apply a force to it. And I'm going to stretch my string to a new length. This change in length is going to equal the stretch. And the force that's being applied, and this is, we're going to give it a proportionality constant that we're going to call the spring constant, times my stretch. And it's negative because this is a restoring force. So it's negative because it's restoring it back, and we get there. But let's look at our force due to gravity. So we've got, these are all the equations that you're going to be, these equations you're going to be using throughout this chapter. And we're going to be looking at friction. We're going to be looking at spring constants. We're going to be looking at our summation of forces. You have lots and lots of example problems. And in fact, it was kind of funny because I was in there and I was doing stuff and I was trying to open up things. You've got over 100 videos and 100 little things that you can look at and PDFs of problems that you can look at. But these are all the things that we're going to be working with. But let's look at our force due to gravity. So I have my object. And we know we have a force due to gravity. And we know that Newton's second law says the summation of forces is going to equal mass times acceleration. Well, what's the acceleration that we have on my block? My block has an acceleration due to gravity. So my force that's being applied to my block is going to be the mass times my acceleration due to gravity. And that's what we call our force due to gravity. Or this is a weight. So mass is stuff. Weight is dependent on the acceleration due to gravity. So I could take an object to the moon. It still has the same mass, but its weight is going to be significantly different. Its weight is going to be different. And we're going to see that when we do the elevator experiment. And we'll talk about the elevator experiment tomorrow. We'll actually look at the elevator experiment as well. What happens if my object has no acceleration? If my object has no acceleration or is traveling at a constant velocity, which it wouldn't have an acceleration if it's traveling at a constant velocity, that means the summation of forces is going to equal 0. And this is the first condition of equilibrium. And we can do a lot with that. In fact, we can do a whole class on looking at forces in equilibrium. So let's kind of look at that for a second. So I have an object that's hanging from a string. We're going to make it a house plant here. I've got the force due to gravity that's being applied. And we're going to say that it has a mass times gravity. We're going to say that this has, it's 100 grams or 100 kilograms times gravity, 9.81 meters per second squared. If I do that, it's going to be 98.1 newtons. Now, if my plant is just hanging there, there's my object, here's my force due to gravity. Newton's law that says objects come in pairs, I have to have another force that's up here. If this were sitting on the table, that would be my normal force, but since it's in the string, we're going to call that tension. We're going to call that tension. And so for this to be standing still, the sum of my forces has to equal 0. And I have tension that's in the positive direction, because remember, these are vectors, minus my force due to gravity in the negative direction has got to equal 0. So the tension in the rope or the string or the chain is going to equal my force due to gravity. I could do something different with a pulley. I have an object on this side of my pulley, and I have an object on this side of my pulley. If I look at this, I'm going to have my tension in the rope. I'm going to have my force due to gravity. And we're going to actually say that I've got acceleration in this direction. So I actually have, this will have a mass times acceleration that's going to go down. And this side, I'm still going to have tension in the rope. I'm going to have the force due to gravity. But now I might have an acceleration that going in this direction. So that's the mass times the acceleration. Because these two things are tied together, this tension and this tension have to be the same. So we can work problems with pulleys that shows that those items are the same. So we start to start thinking about the situations that were given in order to do our calculation of forces. This is one of those cases where you're going to have to develop your own equations. So let's have a boat. So I have a boat here. And we have a force on the boat. And this is a force of 30 newtons. And then we have a force of 50 newtons. and this is 45 degrees, and this is 30 degrees. We want to know the magnitude and direction of the acceleration. And we're going to say our boat is 2,000, or we'll say our boat is 200 kilograms. All right, so we got a force of 50 newtons pulling it this way. We got a force of 30 newtons pulling it this way. And we have 200 kilograms. Well, first thing is, we know that the summation of forces is going to equal the mass times acceleration. All right, well, that's good. But my acceleration is going to have an x component, and my acceleration is going to have a y component. Okay, so I got to deal with that. All right. So the first thing let's do, let's go ahead and let's add up these forces. So I'm going to go ahead and do this. I'm going to do this graphically so you guys can see it graphically. So I'm going to use, I can do that. Okay. I got a 45-degree angle. So here's my 50 Newton force at a 45-degree angle. And then I have a 30 Newton force. And that's a 30-degree angle. Well, one of the interesting things is I can do things head to tail. I can add my vectors head to tail. And I can come up with a force diagram. So there's my 5 newtons, 50 newtons. So here's my resultant force that I've added graphically here. So there's my resultant force. And so we could actually measure that if we had our protractor, but I don't have my protractor, but I can do this a couple of ways. So force 1 is equal to 50 cosine 45 degrees in the I direction plus 50 sine 45 degrees in the J direction. Force 2 is 30 cosine 30 degrees in the I direction minus 30 sine 30 in the J direction. So if I do the calculations here, this is going to be 35.4. This one's going to be 35.4. This is 26.0. This is negative 15. If I add these together, this is going to be minus 10J. Well, it's actually going to be minus, sorry, this is minus 20.4J. And this one is going to be 61.4 I. That's my resultant force. I can calculate the magnitude. That's the square root of 61.4. That's plus. I knew something was wrong, because it was above there, plus 20.4 squared. And this gives me 64.7. And if I go ahead and measure this, not perfect, but I didn't use a protractor, but I'm definitely over 6, so I'm in the right, I'm pretty darn close. So my resultant vector is going to be 64.7 newtons. My angle is going to be the arctangent of 20.4 divided by 61.4. And that gives me, oops, this is, sorry, that's not going to be that right angle. This is going to be the angle that we've got. And it looks like it gives me about 18 degrees. Again, I'm dealing with the fact that I didn't do this with an exact protractor. But you can actually, and that was 18.5 degrees. So you can actually do that calculation. So now I've got my force vector. Okay, my force vector is equal to 61.4 I plus 20.4 J. My acceleration vector is going to be my force vector divided by the mass. So I'm going to get my 61.4 divided by 200 I plus my 20.4 divided by my 200 J. Gives me 0.307 in the I direction plus 0.102 in the J direction, and that's in meters per second squared. And that's my acceleration vector. So we can take these and figure out all kinds of good things. And so we can play with our vectors in order to get there and be able to work with that. All right. I'm pretty sure brains are full.